Hello, and welcome to our next set of notes for mathematical reasoning. We're covering section 11c, which is going to be on the golden ratio and the Fibonacci sequence. So the ancient Greeks claimed that the most visually pleasing division of a line segment into two pieces had this property. They said that if you take a line segment and you divide it, the ratio of the long piece to the short piece would be equal to the ratio of the entire segment to the long piece. So they said the way to take a line segment and divide it the most pleasing way, the place to cut it off the most pleasingly, would make it so that the long side over the short side, here we just label the short side 1 to make things simple. So the short side's 1, the long side's L. They said this ratio, L over 1, long side over short side, should be equal to the ratio if you take the entire line, so L plus 1 is the entire line, over just the long side. If those two ratios are equal, then you've cut this line in the most pleasing way. So that was what they looked at. So writing it this way, where we make the short side 1 and the long side L, you actually get an equation that can be solved because we have just L's in here. So we can actually solve this for L. Now if you solve this and find L, we'll get a specific value, and we actually denote that value with the letter phi. So phi is the length of this side compared to the other side. In fact, in this way we did this right here. I said the short side has to be 1. You could actually have the short side be lots of different numbers. What has to happen though is that the long side has to be phi times the short side. So because this side is L times 1, or just L, so that's the ratio we're going to look for. So the long side should be phi times as big as the short side. So phi is that length, L, how much bigger this side has to be than that side. And we find that the value is an irrational number. Irrational numbers are numbers like pi. They're you can't write them as a fraction. You can only write them as a decimal, and they don't repeat. They're just a never-ending decimal with lots of different numbers. They're kind of irrational numbers. A lot of times people approximate with 1.6 or 8/5, which is 1.6. You know, if you divide that, you get 1.6. But the actual value for phi is 1 plus root 5 over 2. So this is the value. This is what you get if you solve this equation up here for L. 1 plus root 5 over 2, and it's about 1.618. And we'll actually use 1.618 in my lab and on the homework and the exams and stuff. That's the approximation you'll use. I have that on the formula sheet for the exam. So that's what we use for phi. You know, yeah, that's not exact. 1 plus root 5 over 2 is perfect, exact. 1.618 will make a good enough approximation for us. So we call this number phi, we call this the golden ration or the golden ratio. We call it the golden mean, the golden section, golden cut, the divine proportion. Basically, again, this is the Greeks, I believe that this is the best way, the most pleasing way to divide a line segment. So let's say we have a line segment that is divided according to the golden ratio. So it's divided in this way where the long side is phi times as much as the short side. If the longer piece is 12, what is the shorter piece? So using this, we were looking for X to be the shorter segment, right? We're trying to figure out what the shorter segment is. We know that the ratio, long side, so longer piece, 12, over short side, X, 12 over X, this ratio, you know, it's basically the L over 1, the long over short side, long over short. That should be equal to phi, because we said it's divided according to the golden ratio. This should equal about 1.618, or phi. So we can solve this, we actually figure out what X is. The way to solve this is we actually multiply X on both sides. That would get rid of the X on the bottom. So we take 1.68 times X. And then to get rid of the 1.618 and get X by itself, we divide that across. So this actually becomes the expression 12 divided by 1.618 equals X. You get this if you multiply by X on both sides, cancel the X down here, and then divide the 1.618 across. So we can actually find the short side by taking the long side and dividing it by 1.618. That's our methodology here. So we can always find the short side by taking the long side divided by phi. And so here we get about 7.1 or 416. So X equals 7.41. I guess 7 if you want to round to the appropriate decimal place, because the 5 would have us rounded up to a 7. My math lab will tell you how many spots to round. The big thing here is note that if you have the long side, you want the short side, divide by phi. You don't have to do this whole solving part. You can just say, okay, yeah, long divided by phi gives you the short side. Now, some of the homework questions and stuff will actually have you find this number, and then they'll ask for the total length of the line. So instead of just asking for the short side, they say, okay, if the long side is 12, what's the total length? Well, you just find the short side and add them together. 7.417 plus 12 give you 19.417. So the whole length of this entire segment would be about 19. That's something you could do. If you need to find the whole thing, just find the other part and then add them together. Next one, going the other way. So here they say again, it's divided according to the golden ratio, so it has that golden ratio. The length of the shorter piece is 4. The longer segment we'll call y, because this time it's not, the short side. I guess we could have called it L. We'll call it y. So this time the longer is what we're looking for. We know the shorter piece. So this time y is going to be on top because we don't know the longer piece. 4 is going to be on bottom because we know the shorter piece. And again, we know that this ratio, according to this is the golden ratio, should be 1.618. Well, this time to find y, all we have to do is just multiply 4 on both sides, because that will get rid of this 4 on the left side. So y is whatever you get when you do 1.618 times 4. And so if I multiply that, 1.618 times 4, it gives me the value. So it's 6.472. So that would be 6.472. That would be the length of the longer piece. Let's just put up here that this was the short piece. Again, if you know the long piece and you know the short piece, and you add those together, you would get the length of the entire line. So now we know that if you take 4 plus 6.4, you get about 10.472. That would be the length of the entire row or line segment. So you should be ready. If I tell you something has a golden ratio and give you either the long piece or the short piece, you should be ready to find the other piece. It's not too big a deal. You just multiply to get the longer piece. Multiply to get the longer piece, divide to get the shorter piece. Note that it's pretty obvious if you did it the wrong direction, like if you multiply when you should divide or divide when you should multiply, because your length won't make sense. Like here, I start with the long piece. My answer should have been shorter. So I'm looking for the short piece. So 7.4 is definitely shorter than 12, well, less than 12. Here I was looking at the short piece, I was looking for the long piece, so I wanted an answer that was bigger than 4. And 6.4 is definitely bigger than 4. So that kind of helps to make sure you're doing it in the right direction. Okay. Now, ancient Greeks really embraced the golden ratio. Euclid, who is kind of the foundational person in regards to geometry, so basically all the geometry you studied in grade school and high school, Euclid wrote books about it. He wrote his Elements, and it covers pretty much all the geometry we teach up through like high school. If you go on and take like college or graduate level geometry, if you go into more advanced geometry, then you finally get into stuff that maybe he didn't cover, and he covered pretty much everything we learn in school for most people. So he actually provided the first known definition of the golden ratio. So it was the first written definition we found came from Euclid. The mystical Pythagorean brotherhood, so remember Pythagoras, the guy that has the a squared plus b squared equals c squared formula, very famous mathematician. We mentioned him when we talk about math and music. They actually used a symbol called a pentagram, which is a star inscribed in a circle. So draw a 5-point star so it fits, so each point would be on the circle. And that was the secret symbol of their brotherhood. Like they use this as a way to say, hey, are you a member of the brotherhood? You know what that is? If you draw it, be like, there, so yeah, no, I'm part of this group. It was their secret symbol. It actually has the golden ratio in like 10 different ways. One of the simple ways is if you look at the ratio of the sides on this internal pentagon here versus the sides of the external triangles, they have a ratio of phi. So this is the long side over the short side. That ratio is phi. Over here, this is actually the same ratio. If you look at this here, this is the pentagon and this one. So again, this A over B would be phi as well. If you look at this triangle in the middle here, the short side would be out here. This long side is this entire thing from here to here. And that ratio, C over D, is also phi. So that ratio, this side to this side, is phi. There's another one down here, this one down here. This would be the short side, we'll call that F, and the long side we'll call E. And if you did E over F, that would also be phi. And these are just 3 examples, right? This is just 3 ways we have this. There's like 10 of these. If you keep looking and digging and find different line lengths and stuff and compare them, you end up with like 10 different ways where you can find phi show up in this shape. Kind of crazy how often it shows up in there. So you can see why Pythagoras and them were kind of maybe excited to use it, because it exemplified this golden ratio and their idea of like what's perfect or good. Another way to think about golden ratios is to look at rectangles. So we can talk about what's called the golden rectangle. So a golden rectangle is a rectangle whose short side and long side have the ratio phi. So the long side is going to be phi times the short side. Again, like we did with the line, a lot of times we'll call the short side 1, and then the long side is going to be phi times that. So it'd be about 1.6 if this is 1. This length doesn't have to be 1. It could be 10, and then this would be 10 times phi. Or if this could be 5, this would be 5 times phi. The idea is that the ratio, if I take this side divided by this side, goes into phi. Notice there's kind of cool property of these that since the long side here is longer, there's going to be a square inside here. Well, obviously there's always a square inside a rectangle if you cut off the long bit. That's not a big deal. But what is a big deal is this rectangle over here, this guy right here, where this side, so let's say like B over A, this one. So this, A over B, long side over short side, is also phi. So this length and this length make another golden rectangle, because that's another golden ratio. So the golden rectangle always contains another golden rectangle. In fact, you could take this golden rectangle, cut off, length of B, make a cut off another square, and if you remove that square, then the rectangle would be left would also be a golden rectangle. So you can keep doing that like to infinity. So there's this cool property that golden rectangles always contain golden rectangles. So all you do is take a square out, and you're left with a golden rectangle. All right, now one thing you need to be able to do is to determine if a rectangle is a golden rectangle. So if I give you the dimensions of a rectangle, you should be able to tell me if it is a golden rectangle. So my wife is an artist. She sells art prints. They're designed to be placed in frames. The sizes are like 11 by 14, 9 by 12, 8 by 10. Let's see which one of these is closest to the golden rectangle. If I want to check this, I want to see if they're a golden rectangle. Remember that the long side over the short side should be phi, about 1.618. So to check this, all I have to do is take the long side and divide by the short side and see if I get phi. So if I do like 14 over 11, we'll see what that ratio is. And if it's phi, it's going to be about 1.6. So 14 divided by 11. And I actually get about 1.27. So definitely not phi. It's more than 1, but it's not that close to phi. If I do the next one, so 9 by 12, so I go do 12 over 9, always long over short. Divide that, what do we get? So 12 divided by 9. I get 1.3, so 1.33. And then last one, let's do our 8 by 10. So now I'm taking 10 divided by 8. And 10 divided by 8. It's actually 1.25. So surprisingly, none of these are actually that close to the golden rectangle. When I first did this problem years ago, when I first started teaching this class, I thought, oh, it'd be a cool thing to check, because I know a lot of modern things use the golden rectangle. So I thought, oh, some of these standard art print sizes, and these are pretty standard sizes, 11 by 14, 9 by 12, 8 by 10. You can walk into any art supply store and find frames in these sizes ready to go. So I thought, oh, these got to be golden rectangle. Well, actually, none of them are. The closest we can get is 12 by 9. So we'll know that the 12 by 9 is closest. It's the closest to 1.618. But it's definitely not that close, right? It's not even 1.5. It's actually less than that. So the ratio is not that great. And I was kind of surprised to find that out. That was something I thought was pretty interesting, that, all these kind of big standard sizes are not, if I wanted to do a 9 by 12, I wanted to make something closer to the golden rectangle, I'd have to take that 9 times 1.618. And it'd actually be like a 9 by 14 and a half. So if you make something that's 9 by 14 and a half, that would be closer to the golden rectangle. And surprisingly, that's not the typical frame size, which is interesting. Okay, so the Greeks, like I said, were really into this golden ratio. They really like to study, shapes and geometry. Geometry is big with the Greeks. And so they were looking at, building their architecture stuff, and they incorporated, golden rectangles into their architecture. Not just the ancient Greeks, but actually other ancient cultures as well. So, it was a big part of their philosophy of aesthetics. Philosophy of aesthetics was basically kind of the study of beauty and what's perfect and beautiful in nature. They were looking for what's right, what's good, what's pleasing to the eye, that kind of idea. And so things like their Parthenon, so the Parthenon, famous Greek structure, It's actually a little bit broken down, like the peak of the roof is gone now, but the columns and stuff are still there. But the original height you can kind of project. You can figure out that the original height and then like the height across, the width across, do make a golden rectangle. So this height here type and this height here make a golden rectangle. So the width is phi times this height. We actually also see the golden rectangle show up in the pyramids, like the pyramids of Giza. And so what happens here is if you look at like the length from the center of the pyramid to the outer edge, if you call that 1, then the height, the diagonal height, sorry, not the height in the middle, but the height on the diagonal is actually going to be phi. So this height here is phi. So if you lay a line from the point of the pyramid to that edge, that's going to be phi times the length from the middle of the pyramid to the edge over here. And they didn't have to make that phi. They could have made this piece longer or shorter to, make the peak. They could have been higher or lower, but no, they made it phi times this length. It's kind of crazy. It shows up in these ancient structures. Artists use this as well. So the golden rectangle appears in lots of works of art. The French neo-impressionist painter Georges Seurat, mostly, I think his most famous piece was Sunday in the Park with George, probably seen. He used a lot of golden rectangles in his work. There's some people who say that like every piece he ever made had golden rectangles. This one's called Parade des Cercles, or Cirque Sideshow. You can see here that kind of, we talked about earlier with the golden rectangle, how if you cut off a square, so you can kind of see this darker purplish part, cut off that square. Over here you have this green bit on the side, is another golden rectangle. And so we have like that self-golden rectangle within the golden rectangle thing showing up here. And there's actually golden rectangles inside this shape as well. So, again, he worked in that golden rectangle. The works of Dutch painter Modrian, who's famous for his solid color, like square rectangles, included many golden rectangles. So a lot of the rectangles and shapes are golden rectangles. I was looking this up, and basically this piece here, they had x-rayed it to kind of look at the work he did before he actually put his paint down, and kind of the layout, the trace work, that kind of stuff. And they showed that there was a grid that he made that was, based on the golden rectangle. So when he was planning out the piece, he was kind of thinking about those kind of things. Today we see this golden rectangle pop up in lots of everyday items, like I mentioned earlier, so like photos, note cards, cereal boxes, posters, and even windows. So a lot of things that are made nowadays will exemplify the golden ratio. They will be golden rectangles. However, it's actually still an open question. We're not really sure if the golden rectangle is the most pleasing shape, like the best and the most perfect visually. In the 19th century, so in the 1800s, so this has been a question for a long time. People have been looking at this for a long time. German psychologist Gustav Fechner studied this statistically. He basically did a study and had people pick out which rectangle he thought was the most pleasing, the most beautiful. 35% of participants picked out the golden rectangle, which isn't that much, right? That's not even half the, 35% is a good amount, but it's not even half the participants. Less than half actually picked out the golden rectangle. But if you look at the 3 rectangles closest to the golden rectangle, then you get 75% of people. So the vast majority, 3/4 of the people actually picked out something that's pretty close to the golden rectangle. So it kind of seems to point towards the fact that the golden rectangle might be the most aesthetically pleasing. Now, I should say that there are other people who have done their own studies or looked at these studies and have decided that no, this is very much inconclusive. There is no really valid evidence saying the golden rectangle is most perfect. People have said that, part of why we find all these golden rectangles is because we're looking for them. Someone is out there looking to see what we find that has a golden rectangle in it. And so maybe it doesn't have anything to do with those people planning that out and working that in. Maybe it's just that we've been looking so hard for them, we're finding them basically wherever they show up. And it's, that might be an argument. So there are people that argue that the golden rectangle might have nothing to do with beauty, might not be that special. But it's still an open question. We don't know for sure. This is something where there's not a complete proof one way or the other. So if you believe they are, you can for now. We haven't proven for sure one way or the other. Okay. The golden ratio actually appears really common in nature as well. So that might be one argument, is that we actually do find this in nature. One example is what's called the logarithmic spiral, and it's a shape you create from the golden rectangle. So remember how we did that thing where we had the golden rectangle, and you could cut out a square, and then you could have a golden rectangle left over, and then you could actually keep cutting out squares and end up with another golden rectangle. You can cut out more squares, end up with another golden rectangle. Cut out more squares, and you can keep doing this. You actually end up like this with them, like spiraling in like smaller and smaller squares and smaller and smaller golden rectangles. So if you take and you draw a curve from one side of the square, curve to the other corner, and keep doing that. And each time you just hit the next square, you just keep curving to the next square. And you keep doing that, eventually you get this spiral shape. And this spiral shape is exactly the same curve we see in nautilus shells. So this curve here, if you overlay this curve on top of it, you'll see that same curve inside these shapes, these natural shapes. So this spiral is called a logarithmic spiral. So that's the logarithmic spiral. And it's done by connecting the corners. And it closely matches that nautilus shell. It actually shows up in other places as well. So in nature we see it like flight paths of birds and insects. So I was actually kind of saw this the other day. I was out at a lake with my wife, and we saw some of these sandhill cranes flying over us. And when I see geese and ducks, it seems like a lot of times they're on their V and they're just like flying straight one direction. But instead of flying just straight in one direction, these sandhill cranes were basically making this kind of big looping shape. And they were getting further and further in one direction, but they were kind of making these big curves. So I thought that was pretty interesting. That's kind of how they flew. The nerves in your cornea, so like the nerves in your eye will have the same kind of curved shape. There's lots of other examples. So seeds, so the seeds in the pod, you can kind of follow the curve here. You can see that kind of same curve. Galaxies have the same curve in them, so the spiral galaxies. Hurricanes exhibit that same logarithmic spiral. Leaves and things like artichokes and other, succulent plants like this, sometimes will exemplify that shape. So this logarithmic spiral can show up all over the place. And again, it's an expression of the golden ratio. This is something we designed or found out of the golden rectangle, which comes out of the golden ratio. So it pops up in nature, not just in works of art, architecture and art. Okay, might feel like a little bit offshoot, but we'll connect back to the golden ratio in a second. Let's talk about Fibonacci sequence. So Fibonacci sequence, back in 1202, by Italian mathematician Leonardo Fibonacci. He was around in the late 1100s, early 1200s. He's actually known for bringing Hindu Arabic numerals to the Western world. And if you don't know what Hindu Arabic numerals are, you actually use them every day. I actually have them right on the paper. Hindu Arabic numerals are our numbers that we use. So before 1200s, if you were in the Western world, if you're in Europe and Greece and Rome, that kind of place, you would use Roman numerals. The I's, the V's, the X's. That system's not great because you have to use lots of different symbols like combined to make letters, and it gets kind of confusing the way they combine and stuff. Positional numeration is kind of hard. I don't think they really have like place values so much, like all that. So the Hindu Arabic numerals, numbers like this, like a 1202, 1170, they're much more concise, easier to use. They're easy to do things like multiply, divide, do like exponents. And Bonacci, Leonardo Bonacci, actually wrote a book and he talked about like the benefits of using these Hindu Arabic numerals. So we call them Hindu Arabic. A lot of people used to call them Arabic. They actually were originated by the Hindu, came to us through the Arabic peoples. So that's why now we call them Hindu Arabic because of where they came from. So he was one that really kind of got these to the Western world, got them really popularized. So you can thank him, because otherwise you'd be trying to do all your math homework in like Roman numerals, which would not be as fun. Trust me. If you ever try to multiply with Roman numerals, it's not easy to think in that way. Even if you like been thinking about Roman numerals all your life, I don't think it'd be easy. It's easy to multiply just like what we do. But he actually was looking at different problems. So that's unrelated to Hindu Arabic numerals. He has this problem, which led to a sequence we're going to call Fibonacci sequence. We call it Fibonacci because Fibonacci actually just means son of Fibonacci. And so, Leonardo Fibonacci, his dad was also Fibonacci, so he's often called Fibonacci. He was looking at this problem here. So this is his big problem that he looked at. And it's a problem on bunny population. So basically, it starts off, you have a pair of baby rabbits. So you start off with just one pair of baby rabbits, and then you have 1 month to mature. So every month they'll, if you have a pair of baby, it takes a month they'll be mature and they'll be breeding adults, basically. And so after they're adults, then they produce a new pair of baby rabbits the following month. And we're going to say they always produce 2. In real life, that's silly because rabbits are going to have sometimes 5, sometimes 3, sometimes 1. They're going to have a litter, not just like 2. But we'll just pretend that every time they produce a new pair each month and every subsequent month. So just like clockwork, every month they'll have babies, 2 babies. And they'll always be a boy or girl, or that's what we'll assume. Further, suppose each new pair of baby rabbits reproduces in the same manner. So every new pair will have to take a month to mature and then start producing their own. If no rabbits die, we're going to assume that it's a perfect world. There's no foxes or disease out there getting the rabbits. Kind of make it nice and simple. We'll say, okay, nothing dies. How many pairs of rabbits are there at the beginning of the month? So we're looking for how many at the beginning of each month, when they're maturing and they've been born and all that kind of stuff. So we're looking for the number of pairs. We try to make something simple. We don't want to make it too overly complicated. Try to worry about okay, one time they have 3 babies, one time they have 4 babies, one time they have 2 babies. So it's kind of simplified version, but that's kind of typically what we do with mathematics is we come up with a kind of simple version of the problem. So what you saw is the first month, of course, we had 1 baby, right? We could have 1 pair of babies. So there's 1 pair to start with. There's the original pair we start with. After a month, we still have 1 because now they've grown up, but that first month they didn't have any babies because they're babies themselves. Now in the month we have still 1 pair of now of adults, not of babies. Now that they're adults, in the second month they're going to give birth. So in month 3, now we have a set of babies as long as those original 2 parents. So now we have 2 pairs. And then the third month, they're actually going to give birth again. So you can see, now they're giving birth every month. They're going to keep doing that the rest of the time. They're always going to have a pair of babies every month. The babies that they had the first time now have grown up. They didn't have any babies when they were babies, but now they're adults, and next month they'll have babies. And these other babies are still babies. But now we have 3 pairs of rabbits. Now we go to the next month, and the adults are having another set of babies. The first set of babies has grown up and has their own babies, and these babies just grew up. But now we're up to 5 babies. We've moved up to 5. And we look here and say, okay, well, the second set of babies is adults now, so they have a pair of babies. These babies were just born, so they're just still growing up. These adults, original adults, are having more babies. These first pair of babies is having its own babies, and this pair of babies is growing up, and we're up to 8. And you can see there is kind of a pattern here. You start off with 1, and then we have 1 again, but then the next number is 2. Well, you can see that if you add 1 plus 1, you get that 2. And then if you take 1 plus 2, you get the next number, which is 3. If you take 2 plus 3, you get the next number, which is 5. Take 3 plus 5, you get the next number, which is 8. In fact, this continues. You can actually use this pattern. If you sat here and drew all the bunnies, you would see that the sequence does continue, where you can always take and add the 2 previous numbers to get the next number. Like 2 plus 3 is 5, or 3 plus 5 is 8. So I can do 5 plus 8, so the next number is going to be 13. I do 8 plus 13, so the next number is 21. Do 13 plus 21, I get 34. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Do 1 more, so I got 34 plus 21, I got 55. And that'd be the first 10 numbers in the sequence. And every number, so each is the sum, add up, of the 2 previous. Some people actually start the sequence with a 0 at the beginning, because you get 0 plus 1 gives you 1. So you could add 0 at the beginning. For the purpose of this, I'll just start with 1, 1. Like the picture shows. I've got still the picture from the book. But just be aware. Sometimes people start with 0, 1. Some people actually start with 1, 2. I think back in the day that was more traditional for people to start with 1, 2. But start with a pair of babies. I think it makes most sense to start with 1, 1 because the first month they just have to grow up. So this is how we'll do it: 1, 1, 2, 3, 5, 8. So that's the Fibonacci sequence. So this sequence again, it's going to just keep growing and growing. No rabbits are dying, so we're just getting more and more rabbits. Eventually, just fill the entire planet. But it's not realistic. It's a simplified version of the problem. But that's the idea. Every number is the sum of the 2 previous numbers. So how we can express this? If we want to express the sequence, this is what's called a recursive sequence. So recursive sequence is a sequence where you can find the next number of sequence by doing computations with the previous numbers. And what we'll do is we say, okay, find the next number of the sequence if we just add the current number with the previous number. So adding those 2 will give us the next number. So n plus 1 would be like the next one, because it's 1 more. N is the current number, the one we're on, and n minus 1 is the previous, because it's 1 less. So that'd be our next, current, and previous. And again, we add the current plus the previous to get the next. So you add up 2 numbers, you always get the next number. So this formula, I believe I have on the formula sheet. It's kind of a good reminder that when you see a Fibonacci sequence, you should think, oh yeah, I'm adding up 2 numbers to get the next number. Now below, someone took these, your book I should say, took these first 18 Fibonacci numbers. They kind of skipped the very first two because 1 over 1 is kind of silly. 1 over 1 is 1. But they made ratios. They made fractions. So it's okay, like we got 1, 1, 2. Well, there's 2 divided by 1. And then we're just taking the next number divided by the previous number. And then they had 3 divided by 2. And then 5 by 3. And then 8 by 5. And they kept going. 13 over 8. 21 over 13. 34 over 12. 55 over 4. That's as far as we got. If you keep going, you get bigger and bigger numbers. And what happens is with these ratios, because you're always doing the bigger number over top of the smaller number, you're getting, what you'll see is that it started off kind of jumping around wildly, but as you go, you can see they kind of settle down on like 1.6. As you get further, they settle on 1.61. As you get further, they settle down on 1.618, and then 1.6180. And what you see is they're actually getting closer. They're approaching, as the values get bigger, as you get further down the sequence, they're approaching phi, which is that 1.6180. So on and so forth. And that's what they found. They figured out that this golden ratio that we talked about earlier, this golden ratio, this golden section, this value of 1.618 or 1 plus square root of 5 over 2, the proper version of it. That's what happens if you look at these, sequence of Fibonacci numbers and you make ratios up. You get closer and closer to this eventual 1.618. And we've actually found this in some other sequences too. There's a sequence that's kind of related to Fibonacci that's called the Lucas sequence. Your homework mentions it. So Lucas sequence actually has the same property, whereas you get further down the list, you get closer and closer to this ratio being phi. And it's just kind of crazy that this pops up out of this problem that to do with like solving the population of rabbits, and here we are with the golden ratio showing up. Okay, now what I want you to be able to do with the Fibonacci sequence, kind of the main thing besides like counting it, listing it, right? We did that. We like listed some Fibonacci numbers. You should be able to do that. The other thing is, if I give you some Fibonacci numbers, you should be able to find the next number in the sequence. Yes, you could start from the beginning and count your way out. Here I'm only going like 1920. You could go out 1920 numbers, but that does get to be kind of tedious. So the simple way to do it is to say, well, if I have two numbers, the way to find the next number is just to add them up. So the 19th number, which is 4181, plus the 20th number, which is 6765, will of course give me the 21st number, the next number in the sequence. So I just have to add those together. Not a big deal because that's how the Fibonacci sequence works, right? The whole idea is that adding two numbers gets you the next number. So the next number is going to be 10,946. So that would be F21, or the 21st Fibonacci number. We call these Fibonacci numbers because they're part of the Fibonacci sequence. Not all numbers are part of the Fibonacci sequence, but we counted like 1, 1, 2, 3, 5. We skip right over 4. We skip right over like 6 and 7. So a lot of numbers are not Fibonacci numbers, but there's this infinite list of Fibonacci numbers. We kind of treat them as special because they're part of this Fibonacci list, or we think of them as special because they're part of that list. So this would be the 21st Fibonacci number. What about instead of trying to find the next number, we're trying to find a number between. So here I have the 24th number, which is 46,368. And I have the 22nd number, which is 17,711. I want to find the 23rd, so I actually want to find the number between those. Well, the trick here is remembering that if I take, the 22nd plus the 23rd, I get the 24th. We know that. That's the whole definition, right? Add the two numbers, get the next. But that actually tells us that we can take the 24th number, subtract the 22nd number, and by fact families, when you learn about addition and subtraction, remember there's a relationship here that if you take the big number minus one of its parts, minus the small parts, you get the other parts. We'll actually get F23. So the idea is if you want to find the number between the numbers, we can subtract. You just take the bigger number minus the other number you have, and you find the number between. So I'm going to take this 46,368, which is the 24th number, and subtract the 17,711, which is the 22nd number. And what I'll get for my answer is going to be the 23rd number. So I'm going to do 46,368 minus 17,711. And I get 28,657. So 28,657. And you should see that is between 46,000 and 17,000. And this is the value for the 23rd Fibonacci number. And it is a list of numbers. They are always the same value. So technically, yes, you could memorize all the Fibonacci numbers. I definitely wouldn't, because that's a lot of numbers to memorize. It's probably better to be able to figure this out and go, okay, well, if I need the next number, you just add to get the next number. If I want to in the middle number, or if you want to go previous, you just take the bigger number minus the smaller number, and that'll give you the previous number, or the number in the middle, in this case. Okay, Fibonacci sequence actually also shows up in nature. Besides just having the golden ratio built in, it has some places where it shows up. Lots of examples. So the heads of sunflowers, you get sunflower shapes like this, they have clockwise and counterclockwise spirals superimposed on each other. So you can kind of see that there's these like clockwise spirals, and then there's also counterclockwise spirals in the middle like pieces here. And so they look kind of like this if you just take and like kind of graph the points. You get the basic shape where you have these spirals going one way and spirals going the other way, and they interlaced or intertwined. Well, the number of little pieces or florets in these, the number of florets is actually going to be a Fibonacci number. So when you look at these things, if you sat here and counted all the numbers in each one of these pieces, you always end up with Fibonacci numbers. Kind of crazy. The arrangement of leaves on the stems of many plants exhibit the Fibonacci sequence. So look at this one, like we start off the first like layer, there's one leaf, and then there's one leaf here when you've got to 2 branches. When you get to 3 branches, then there's actually 2 leaves. When you get to more branches, you've got 5 leaves and 8 leaves. So if you look at the number of leaves, you can see this pattern, and it's actually the Fibonacci pattern. So that the numbers of leaves on stems can be a Fibonacci. This is, I think, is a graph showing like stinkwort, is the plant called. We also find Fibonacci numbers spiraling on pine cones and pineapples. So here's an example of pineapples. So basically they drew a line and they kind of made an angle and said, okay, here this line has a bunch of parallel lines. You can kind of see how you can make parallel lines on there. And you end up with 8 rows, which is another Fibonacci sequence number. If you make a little bit steeper angle, so you're not going this flat, you go a little bit steeper, then this angle right here actually makes 13 rows. So there's actually 13 count going this way, another Fibonacci number. And if you go as steep as you can, here you notice that you actually end up really steep, you end up with 21 rows. So if you're going around the pineapple like this, you'd have 21, again, Fibonacci numbers. So these Fibonacci numbers show up all over the place in real life, in actual nature. We find them in nature. So kind of crazy. Like, again, we don't know for sure, exactly what drives all this, why we have all these logarithmic spirals, all these Fibonacci numbers show up in nature. I believe there's some people that kind of have an opinion that it has something to do with like packing density, trying to get things put in tightly and efficiently. And so that might be something you can look into if you're curious about this, but that's it. I did want to pick a note, so I did post a couple of videos. During my in-person class, I like to show some other videos that kind of reiterate some of these topics. One of them is actually a Donald Duck cartoon, so I did add those to the YouTube playlist as a way for you to kind of watch those yourself. You can watch or as much as little. Those things weren't necessarily like covered directly on like homework or exams. All the exams will definitely come from the notes. But if you're curious about this, if this was interesting to you, I definitely recommend. Donald Duck Mathematics Land talks about the golden ratio, and the gold section actually talks about Pythagoras, the pentagram, about how he looked at music and the octaves, like we talked about in the music section. So it's kind of cool that they talked about all this in this old like Donald Duck cartoon. It's from like 50s, 60s, so it's been around for a while, but they were already kind of studying this stuff and incorporated it to a cool little cartoon. So, and then there's other videos I posted too, some that talk about like the tilings we talked about last time, and videos that talked about the music and how they make digital music. So I'll put those in, have those included for you. So, all right, that's it for today. I'll see you next time when we do our last section, which is mathematics and poetry.